Okay, so since we're going to use induction quite a bit in this course, I thought it would be nice to first have a freshener about induction, because it's a topic that students have quite a bit of problem with it, and part of it, I think, is that people learn induction in a very formalistic way of how to write it, right? You know, it's like filling a form. And in the process, people forget that it's in fact, you know, at some level, it's a simple thing to write once you get the basic idea. And I think somehow, in a lot of cases, people just don't understand the basic idea very well. So let me try to explain it to you. And the way I like to think about induction is in fact a very algorithmic way, right? So the basic idea is that we're going to have the basic induction, we're going to have some claim about numbers. And it can be a very simple claim about numbers. So let's, for example, write claim any number n, any integer n can be written as a sum of a distinct power of 2, of a distinct powers of 2. By the way, I should say that this the ancient Egyptians knew about powers of 2. In fact, there is this Rind papyrus, which is 3,700 years ago, where they do more complicated thing with powers of 2. Essentially, they use power of 2 of way of doing multiplications. So this claim was known for almost 4 millennia, maybe more, which is kind of impressive. Okay, so you look at this claim and you want to prove it, right? And I really want you to think about this proof as, you know, writing an algorithm that verifies it, right? A recursive function, if you want, right? So let's call it verify n, right? Or maybe I should say proof with double quote, because we will rewrite it later in a maybe more formal way. So verify n, right? This is the function. We get the number n, we need to verify the claim. So, and this function is going to be recursive, right? So let's start with the easy case, you know. If n is equal 1, then the claim definitely holds, right? And in fact, think about our function as returning this representation. So the representation is going to be 1, because 1, of course, is just 2 to the 0, right? So maybe I should write it here. 1 is just 2 to the 0. Okay, so that's easy, right? And if you want to think about all the integer numbers as this array going from, you know, 1, you know, 1, 2, and so on, like this infinite array, you can think about this, that we first verified that the first entry in this array is indeed true, right? Think about the verifier as an algorithm that needs to fill up this array, right? So if we call it on 1, it says yes, the entry is 1, and in fact it can just turn on this bit, and in fact if we think about this representation, it can hang from it the representation, right? If we think about this as an algorithm. Okay, now the question becomes, you know, we can of course repeat this process, right? If n equal 2, blah blah blah, then return 2, right? This whole thing is a comment, and we can of course continue in this fashion, but at some point it becomes very boring, right? So this is those first numbers are this base. This is when you speak about induction, this is the base of the induction. We speak about recursive programming, this would be the edge cases or the base cases that you have to handle. But now we want to handle a general number, right? Now, conceptually, let's assume that I call the algorithm on n, right? And I already, verified the claim for all the smaller numbers, right? So if you think about it, in this array, all the entries are filled, they are marked as true, and for each one of them, think about having this representation as a sum of powers of 2 given to you, right? And now we want to solve the problem for the number n, right? We want to do this for n. Well, one way to write n, right? So the fact that I assume that we already verified the claim to all the smaller number than n, this is called the induction hypothesis, right? Now in the recursive algorithm, you don't write this explicitly. The fact that you assume it's true, it just you implicitly use it when you do the recursive calls, right? So so in this case, right, we know that all these numbers smaller than n, there is a representation as a distinct sum of powers of 2, and now you can always write n as 1 plus n minus 1, right? Or if you want in our language, we can write representation of n, right? It can be represented as 1, the string 1 plus, and, whatever representation of n minus 1. Right? Or if you want in this, so I call I think I call the claim the function verify, so I should do verify here. Verify n returns us whether or not n can be written as distinct power of 2, and also it represents the string, right? So for the representation of 1, we called verify of n minus 1. This gives us a collection of powers of 2 that their sum is n minus 1, and we add to this collection the string 1, right? Because we just need to add 1 to it. Of course, rep is going to be a collection of string, right? And now a collection of powers of 2, and now the idea is that look on two strings, right? Look on this collection of strings and observe that what can happen if rep has all distinct terms, then we are done, right? Okay, so the hard case is when we have two terms that are the same, and now we're going to do the following. While rep has two terms that are the same, okay, what are we going to do? We're going to, replace two distinct terms, two equal terms by their sum. Okay. So maybe I should do an example of what I mean here, because this is not very clear, right? Okay. So 1 we know is 1. 2 is of course 2 to the 1. This is the base cases. Now think about 3, right? What I said is that represent it as 1 plus 2, right? 2 we already know how to represent, so we get a representation 1 and 2. Okay. Now let's look on the first interesting case, which is 4. 4 is 1 plus 3, right? So we get a representation of 1. You know what, let me just write it as a set. 1, 1, 2, right? Because 1 and 2 is a representation of 3. And now I have two elements in this multi-set that are equal, so I can add them up. right? So I replace 1 and 1 by their sum, which is 2, and I get 2 and 2. The important property here we use is that if you take 2 powers of 2 that are equal and you add them up, you get a new power of 2. And then 2 and 2, again, you add the 2 power of 2 and you get, of course, 4. And at that point, we are done. Okay. And now we'll just return. So it would be this essentially this inductive proof as as a recursive function, right? And in particular, we can, if we think about this array, if you want to print, or if you want, we want to say the array is true, right? The claim is true. Okay. Now, of course, the interesting question here is why the while loop always stops, right? And this is in fact, in some sense, what lies below under a lot of the inductive proof. What happened here is that this while loop essentially, every time you run it, the set of distinct power of 2 you have in the set of elements that you have in your set decreases by 1. We start with a finite set. Every time the loop runs, the number of elements decreases by 1. So sooner or later we are left with one element, and then it's definitely distinct and we will get out of the loop. So this loop runs only a finite number of times, which implies the correctness. Okay. Okay, so this was the the hand wavy write the proof as a code kind of proof. But now let's try to write it as a formal proof that is kind of more in the classical way of writing it, right? So proof. So now we want to say base of induction. Claim is true for n equal 1 and n equal 2, right? Because both 1 and 2 are just can be written themselves as power of 2. Okay, and now induction hypothesis. Induction hypothesis is just, in the language of this, what we did above, is just saying, when we fill this this array, right, verify that every entry in this array, the value is true, the claim is indeed true, we already fill the first n minus 1 entry of this, right? So the claim, assume the claim is true, assume the claim is true for all numbers smaller than n. Okay, and now we need to do the inductive step, right? In the inductive step in the language of recursive programming is, and we're going to do it here, right? So here we said that the claim is holds for all numbers smaller than n. Inductive step for n, right? We need to prove the claim for n. So here's the argument. N can be written as as 1 plus n minus 1. By induction, n minus 1 can be written as a sum of distinct power of 2 right? And now right, so we need the set. Let S be the set of these powers. Okay. And let T be the potentially multiset T equal to S union with 1, right? Because we added the number 1. Okay. Now, if all the elements in T are distinct, then we are done. Then QED, then claim follows. Otherwise, replace any two copies of a number x in T by 2x. Since T is finite, this replacement process stops, and T is the sum, is presentation of n as sum of distinct power of 2. QED, right? And here the proof used what we really used during the argument. If you look at it more carefully, we used two properties. First, the sum of elements in T is always n. So that's one property we use. And the second property we use is that the sum of two powers of identical powers of 2 is a power of 2. So we're going to have a lot of examples of induction throughout the course. So this is just a kind of a refresher about how to write the induction. And usually we will have, you know, structural induction. So we'll not do induction only on one numbers. We'll do induction of pairs of numbers or on lists or graphs. So things are going to get more complicated. But the important thing to remember is this idea that inductive proofs are really, what you're really doing at some level is you're writing this verifier code, which is recursive, and you verify that it works for some base cases, and then you use some kind of divide and conquer, usually very simple divide and conquer, to break it into smaller instances and then put it back together, which is a recursive step, or the inductive step if you want, and this is it, okay? And at some level, you know, writing the induction proof, the exact wording you use and so on doesn't matter, as long as it's clear that you took care of those three things, right? And usually it's useful to do them in this order, right? To say, okay, here are the base cases, here is what we are assuming that the cases that we already we handled, and here is now how we prove it for a bigger input, right? And this is really what's going on. As I said, we will see a lot of examples, and hopefully it will become clearer as the course goes along. Thank you.